right? Okay, so now compare this. So that means two signals. Okay, exactly. The two signals are this S1 of 2, S2 of the BPS case like this, and dpt is equal to bit duration. And this is the equation which absolutely, which I mentioned in the last classes. This is ultimately used in the equation for BPSK for representation 1 and 2. And any signal of this will be consist of energy of the signal and basis function of that. Okay, when you compare this equation with the basic equation, the basis function phi 1 2 of this, phi 1 2 phi 1, that is a basis function of the S1 of 2 to transmit the message of 1, and S of pi of 2 is a basis function of S of 2 is like this, and this is the basis function which will be multiplied to the energy of the signal before transmitting BPSK, and this is the function through which at the receiver we'll able to identify. Okay, so now how this exactly? So as we mentioned that the receiver will identify the symbol 1 and 0 with the help of what you call it as signal space. Look back to it's two signals. S1 of 2 will be used for representation of 1. S2 of 2 will be representation of the 0. So S1 will contain positive EB and S2 will be contain EST minus square root of EB. As I told you, that receiver will check out whether this situation, that is absolutely EB will falls in the region. That means if the signal is falls in the perfect region of the phase, that is plus EB for S1 or 2, then the receiver will deduct that information, whatever the received information is, 1. If it is not falls in within the region of the plus E square of EB, what will it is assumed the deducted information is 0. In a similar manner, S2 of will be false should be within the minus of square root of EB, okay, indicating that. Okay, exactly indicating that, indicating the received information is this. That's all important. The signal space, as I told you, we receiver will plot that signal in the elicited spaces to identify the signal received will falls within the region defined for it in the signal space. If it is false within the region of the signal space it defined for it, then this receiver will deduct that information is whatever the information deducted is perfect. If not falls in that region, will go out of other side. Similar S of 2, S2 of similar both the cases in will happen S1 of 2, S2 of. Look back, S1 of 2 in the last equation I mentioned it plus square root of EB. That means with the S1 of 2, that is representation of 1, which is representation of plus square root of E into phi 1b within the signal space of this, then we once it we identify that it is false in this region because look back class, and it is called as though whatever the information deducted is perfect. In a similar manner, if it is a stuff 2, let us say the minus E squared of EB into E to go into sine of phi t. So if it is false in this region, that is exactly look back reason 2, we mention it, that is deducted signal is 0. So look by S2 of 2 will be representation for what you call it as representation for 0. S1 of 2 will be representation of representation of binary signal within the positive phase, where exactly for S2 is minus phase as that of the what this regions. Okay, so now once is that, and these are the part which I explained already, simple, because S1 will consider the basis function. If you say this is look back, this is yes basis function, this is exactly basis function, and this is exactly the information changes exactly. So look back how this, so that means that means as per the discussion what we have found, S1 of 2, this is the, let us say how this is sequence of generation, that is called PSK transmitter. What is exactly the PSK transmitter? The binary sequence. See, very important, I mentioned in that the binary PSK signal should be a polar based, polar non-written Z score. That we have mentioned what is polar non-written Z, that is absolutely that will be converted like this and in this form. Once this comes, as I told you that before any signal is sending across AWG channel, it should be multiplied the basis function. So the basis function will contain phase and frequency of the carrier wave. This is the information, and we can say the basis function is as simple as a carrier wave. Now, right now we can understand. So S1, this whatever the input comes here after, that is polar enzo, which is the binary sequence of this binary data will be multiplied with the phi 1 of t, that is exactly the cosine wave, that is a cosine wave, that is a carrier wave. So yes, so that whatever this will be multiplied, and generation of the binary PSK. What will happen once this signal binary sequence is multiplied to this? That means this signal will be within this signal depending upon the phase changes, the different phase for 1 and zeros, and that will be generated the analog signal for binary PSKs. Very clear. So similarly, as I said, BPSK coherent deduction. What exactly the coherent deduction? Absolutely, I mentioned it. Coherent deduction. Okay, exactly. So coherent, whatever the input is coming, and it is multiplied, and over the time period, the decision will take one. As yesterday classes, I mentioned it. Choose one. If it is this, okay, exactly. This is look back. Received input at the receiver, and this is a 512. It's locally generated. We have given the information about the what is exactly the phi of this while designing to the receiver, so that the receiver will generate phi 1 of 2, phi 1 of t for, let us say, s1 of 2 comes, so that is x1. So x1 for x of s1 of t will multiply to the pi j over the time period. We'll get back to some information, and thresholds, this voltage will be fed back, and this threshold voltage will be compared with the decision devices here. If it is, this is greater than this, obviously this is greater than this, obviously only 1, because we are sending the information 1 and zeros exactly. So if it is 0, okay, exactly, if this is the less than this, obviously you can understand this is has to be less than that, and the chosen this is exactly this what I call BPSK coherent deduction. So now when we come back the decision rule, so for example the decision rules, because as I mentioned this, so if it is the in the one of the decision rule, will apply the signal spaces, the observation vector, that is a received input, that is a x1 for small s1, x1 should be of this L of, this is exactly we call it as maximum likelihood. This is absolutely for a purpose of our designing. Okay, so this is what exactly. Now let's go for what is exactly what is this is exactly the seal, what you call region space, which you mentioned for this BPSK. This is all I explained. This is a simple aspect. Now let's come back here. Look back. What is the probability RF? I mentioned it. See, look back. S1, the information will be sent, will be multiplied with the basis function of the transmitter. It will be sent across the channel. Please maintain it with channel. The noise is constant, but still noise is getting some variables. So some get variances because of variance factors. So that means we have to analyze the signal flowing the AW channel through the random nature of the probability density function. The receiving information is correct or not. Okay, so for example, it is a conditional probability f of x1 x of z. This is absolutely, this is the equation which you might find it, and this is already explained everything. What is this? Okay, look back. This is, we got it, and final equation of this. Okay, so this is the p10. That means absolutely here the sending information is 0, and expected probability of error is this. That means probability of error of this equation, q is equal to square root of eb into t. So now, so we are derived. So because this is an average, last class I just explained, I'm repeating for 5 to 10 minutes because it's very quite necessary for this. This is P is equal to average probability of symbol of error by the receiver. Q is equal to 2B by N naught. Okay. So now let's come back to power spectral density. See what we are power spectral density. See, look back, power spectral density, absolutely power spectral density of the PSK. Okay, exactly. The power spectral density of the this, okay, exactly, all right. Power spectral density of the PPSK gives the variation of power f omega. See the Zubaks, what will happen? See, what is exactly that? We protect the information, binary information, that is absolutely the carrier waves. That means we protect whatever the carrier wave. That means whatever the information, we'll put it across the frequency of the carrier wave. The frequency of the carrier wave is maximum within this area. More power is concentrated. That means more signal will be concentrated in this. That is exactly we call it as power spectral magnitude. So for PSD we call it. That is also called as power spectrum. When you plot this information, we'll get back to this. This is basically depends upon the what? And the magnitude and the energy of the signal along with what? Basis function. Look back here. For example, S1 of 2 is the information we are sending across to the channel, which multiplied to the basis function that before transmitting it to transmitter. So which is that the basis function of this. Now how this function, how exactly this will be shaped? This shape, for the shape of this will be identified, we call it as gate function of a pulses as per communication department, which is defined by this equation. By leaving the phase equation, we will take the magnitude of this. Within this, the gate function, the gate pulsing function, we call it g of t is equal to square root of 2b into dv. Simple, otherwise this is no derivation is there. As just for a practical, since we are at the beginner of the communication level, we should understand that how these signals absolutely shaped by which kind of a function as per that communication purpose, which is given. The shaping of any kind of a pulse is given by when the g of t. When you compare this with this equation, because this is has been plotted for this equation, and the getting pulses, that is the behavior of the magnitude of the pulse, will give like this. Okay, so now the magnitude of this absolutely all these are the point which I explained in the note, which you can same thing. And now this is what is exactly the magnitude. Okay, what is exactly the magnitude? Magnitude, absolutely, it is given by this fact, magnitude of that. Now let's go back. Quadrature phase shift, what is called QPSK. QPSK is another form. Okay, exactly, is another form of the, what do you call it, another form of the QPSK. See, just before taking that, I mentioned it. I explained again another 5 to 10 minutes because of last class is very important. See, quarterly phase shift, we call it as QPSK. See, look back. In this step, what will happen? We use the two signals. Okay, two signal of a carrier phase for representing one symbol and another for another symbol. Okay, for example, one, if you say cos omega ct will be used for, exactly, will be used for will be used for represent 1, minus cos omega ct will be used for 0. Please mind it, in BPSK, within the signal of the carrier wave we change that. Where exactly here? No, we pass the different signal itself for one representation of one symbol. Let us say we are going to represent, we are going to send the signal 1. That means one carrier wave will be sent. That is absolutely with a phase cos omega ct, where that is absolutely, we can say, positive phases. Okay, when we, let us say that I wanted to send the information 0, then I'm going to use another carrier wave cos omega ct, which is anti-phase with respect to the cos omega ct, which represent the, within which it contains the what, the information that is one to be sent. That is exactly we call as quadrature, because two signals which are anti-phase, that means totally exactly anti 90 degree towards each other, and we call it as quadracy, because cos and sine absolutely or anti-phases quadrature together, and hence we call it as quadri-phase shifted. This kind of a shifting key, phase shifting key, that we shift the phase, we shift the phases of the carrier wave in order to represent the binary numbers 1 and 0 with the help of the different phases as a different signal, and we call it as quadri phase shifted key, we call it as QPSK. Look back here, very simple. The quadrature phase shift key which is given via is this forms. Look back here, look back. See, this is S1 of 2, I mentioned it to represent the 1. So this is exactly the carrier wave will go, and it will be this S1 of 2 cos omega multiply. That means that this will come and it will be placed within, exactly within this. And similarly here, exactly S2 of t, let us say S2 of t, we are going to represent S2 of t 1, which will be multiplied to this, because when you take cos omega c, it will be, so will you correct the phase shifter, negative phase shifter, that means it convert the phase shift. And absolutely we can say that this cos omega ct will come 90 degree phase shift towards, and it's get added together. Okay, so we'll get back to what, one, absolutely one signal. So the quadrature amplitude, see, QAM is equal to what, total for S1 of t is cos omega t, S2 of t is sin omega c. I just mentioned because you will come back to the how exactly generation. This is only for a better understanding of the point, how the signal will be transmitted. Exactly we call it as this kind of, this thing also called, this type of modulation is also called as quadrature amplitude multiplication, because we are going to multiply the signal to represent the signal 1 with the help of the cos omega ct. We are going to multiply this signal S2 to represent 0 with another one, will absolutely that is quadrature is S1 of 2 to cos omega ct plus S2 of into sin omega ct. Okay, so look back is, this is absolute I mentioned here. See, as for the definition of the binary information that about the message symbol is present in the carrier, I told you is very simple. In general, the phase of the carrier takes one of the 4 points in a carrier. The phase may be, see phase, we have mentioned it exactly pi by 2 quadrature, but phases, you can use different phases also. So pi of 4, 3 by 4, 5 by 4, and all these places are equally spaced. Please keep in mind, you can use a pi by 2 between the cos omega ct, which is represent for S12 minus cos omega t, but equally they are spaced. That means if two these spaces are used, it should be what you call 90 degree, or it may be 45 degree, it may be 354, whatever we can use it. Okay, so that means let us say this is a transmitted signal for S1 of t. See, this is a S1 of t is equal to what exact? This is S1 of t EB in phi 1 t, that is EB is energy basis. And look back here, this is the represent BPSK signal, the same thing, called EB2 to cos omega ct, and generally we can represent, because only in these cases, see look, S of t is a basic signal equations here, which will be used with the different phases for representation of that. So I can represent the QPSK signal, SI of t, the energy of the both the signal are common. Look back, very clear, the carrier amplitude of the both the signal, but both the carrier wave, which absolutely was for representing the different symbol, will be the same. Only the phases get changed. That is why the amplitude, that is an energy, that is a signal information, is absolutely mentioned square root of 2e into pi t. Into 2e by t into this factors cos of 2 pi ct plus 2i pi minus pi by 4 will be indication for what exactly with the phases of the two equation. So QPSK overall with the different phases, QPSK signal can be generated from this equation. Look back here, this equation, 0 less than or t less than or equal to otherwise. Okay, 0 otherwise. So this is quadrature because 90-degree phase shift together, but where exactly in the, we can use also 5 by 4, 3, 5, but all are equally spaced, because why this point will come back when I'm talking about MRA FSK. Okay. So this is the equation for QPSK, you must understand, because how is this derivation? Each equation S1 of t will be represented for 1. It should be multiplied energy of the signal. Energy of the signal is given by square root of EB into phase functions. In a similar for S2 of t, the energy of the function is to be multiplied with the phase function. The phase function of S2 of t, in generally we can write the any kind of the signal of the BPSK. So for the BPSK, we know already this is the BPSK here, but this BPSK will be converted into what? Exactly QPSK by adding what exactly? The shape term into its factors. So when you say, when you add this phase term into it, it automatically the equation of the BPSK will behave as like a QPSK. That means we can generate two signals by changing the what? Value of I, because I, let us say I is equal to 0, what will happen? It becomes 5 by 4. That means 1, 2e, 1 for cos omega ct, another one what? Cos omega ct plus 5 by 4 for representing the zeros. Okay. So now this is absolutely, you know, what is the energy of the transmitter? T is equal to bit symbol duration. That means you're transmitting the messages in a bit duration TB. F is equal to carrier frequency of this. Okay, exactly. So this is what, okay, exactly. See, look back, very important point here is absolutely here. Since the frequency is an integer quality, say frequency, omega is NC by T. Okay, so carrier frequency. Look back here, very important. See, if you say two values, okay, so this is integer value. N is what is a phase value? You can generate multiple of phase values. So for quadrature only two, but when you come back to the realistic approaches, when you mention SI of t is equal to, that is the equation of the QPSK as square root of EBT, square root of EB into cos of 2 pi c into 2i minus 1 into what? Pi by 4. I is equal to what? 1, 2, 3, 4. Absolutely here you mention it. So you will get back to 5 by 4. That means the I get changed depending upon the integer value. That is 1 error. So when you say integer has been mentioned plus or minus 1, plus or minus 2. That means for every one you mention, there is a two values to 2. If you mention one value of n, one value of n or I, let us say if you say n, I is equal to one value, it becomes 2 because it's an integer. So that means if you the positive for each value of n, there is a two values, one positive, one for negative. That means if you n is equal to 1, there is a two symbols, either 1 or zeros. So that means n is equal to 2, n is equal to like that. That means possible one. For example, let us take now n is equal to 2. So possible value for any two symbols now. Let us say two symbols we are sending. That means one for S1 of t and two signal. Second signal is S2 of t, which is true exactly we're sending across to the quadrature phase. Okay. So S1 of t will be represented, even though it is one, it can be represented 1 0 also, or otherwise it also represented what 0 1, because there is a two aspect. That is exactly we call die bit. Very important, please make note. The frequency, carrier frequency is equal to LC by 2. And that means it takes the integer value. Okay, because you are going to generate the different phases is required for QPSK, because as in QPSK, what will happen? We are going to, okay, in QPSK, you are going to do that factor with respect to so many, we are going to generate the signals which is required for QPSK signal, as because QPSK demand two kind of signals will be there, for one for transmitting to one and S2 of t is equal to exactly 0. So now let's come back to space diagram of our QPSK symbol. See, this is absolutely this equation which I mentioned it, expanding by this term, absolutely with this term. When expanding equation for this equation, see, cos pi by 4 will become what exactly? Okay, cos pi by 4 really, cos pi by 4. Okay, when it expands, that is this term, this is can consider of 2p pi c 2i minus 5 4 as well cos of a plus b formula. When you apply the cos of a plus b formula, cos a, cos b, and sin a, sin b. So this is expansion. We'll get back to this. Okay, exactly. We'll get back to this. That means here very important here. You know the BPSK. Absolutely, this is a BPSK1 signal, because which we mentioned is cos 580. Comparing the equation, this is the original equation, and this is the BPSK equation. This is exactly what QPSK equation. QPSK equation is exactly we added with the face of this of this BPSK with this what you call pi by 4 2i minus 1 pi by 4, because in a PPSK, okay, and exactly in the PPSK which require QPSK is required two kind of a signal. For one signal is required, one for generating or transmitting one, and another one is exactly we call it as what another call transmitting the message is exactly zeros. Okay, right? So here okay, uh, right. So now, okay, exactly. So that means pi 1 of 2 to cos 2 pi ct s1 of exactly here. So this means exactly when you compare these two function, we have a two different. This is one for a phase. This is another one for the phase difference is this much. So that means exactly we can say that here cos, okay, pi of t. That means we can say we can conclude that S1 of t has a 4 messages, since this is plus or minus two values, plus or minus what exactly two values. The one is for one carrier, another one is for sign terms. For each signal will having a two messages, and we are represented in these forms. Okay, so that means all the four messages, one for example, four messages for each phase, for each symbol there will be two values for each symbol. For this is for x1 of t, this is for x2 of t, 1101 001, and phases absolutely get changes and their value, which is exactly plotted in the word signal characterization of the QPSK. Okay, exactly. This is look back here. The first point will come message 1, which is absolutely 1 1 with a phase difference y. When we come back to the phase 0 1, with absolutely called as message 2. When we come back to this M3, which will exactly this value, 1 0 will absolutely this. Right? This is absolutely then QPSK form. What is exactly the QPSK forms? Look back here. As I mentioned it, even though we are going to send one, but you are going in reality, we are going to send a 2 bit. For example, S1 of T, we are going to send a 1 bit, but instead of that, which will in reality it will have 2 bits, because the frequency of the QPSK takes an integer value, because integer is mentioned plus or minus. For one value, there is a one positive, one negative. That is why we mention is that two information we call it as die bit. 0 1 is called die bit 1, die bit 2, die bit 3, die bit 4. So look back, we have mentioned it here exactly how the QPSK forms will be there. See, let us say this is the information you are generating from. This is for one odd, even, and odd, because let us say two phases. One signal is absolutely Okay, two signal is absolutely from phase signal. Okay, exactly. Two signal is okay. Two signal is this one, 0 1 and two signals. So this is for two, S1 of 2, this is the one bit, this is another bit, S2 of 2 for another one first bit, S2 of 3. This is, let us say, you can assume this is R or this is total. How the QPSK generate? This is the for taking the odd bit, 1, 3, 5, 7 bits. We call it as odd number sequences. When you take the even number 1 0 1 0, this is exactly what even number, and once this is exactly S1 of 2, S2 of 2, and adding together we'll get back to QPS. You see, this is simple. Very important, you should maintain why these two bits, even though it is one bit, for each symbol it will have a two bits. That is why exactly this is absolutely called as here. So how is the generation goes in the block diagram of a QPSK? Very simple, binary data, because binary data is required. Polar level, here it will convert into that. Now what you call it as demultiplexer will generate a will generate a two signal, what do you call it, sir? Two signal, that is S1 of, okay, two signal here, that is A1 of 2, that is S1 of 2, that is simple. And this signal will be multiplied what? Two phases exactly, and QPSK signal. Very simple here. This is exactly called QPSK transmitter. Okay. Similarly, we'll have a what you call it as what you call coherent deduction, because I mentioned it. Coherent deduction is the only possible approach here. So you look back, this is the coherent deduction. This explains. This is the received signal X of t. As I told you, it will be mentioned by what exactly? Phi of 1 2. There is a basis function locally generated. For each signal will be multiplied by phi 1. This look back, phi 1, that is a basis functions. We mentioned the frequency and the basis of this. Each one will have different phases here. So that means one signal will come, another signal, definitely both together in a QPSK has to be different phases, and this will be because since signal will be taken over by time duration, bit duration, because symbol will be generated at every t duration. That is why we integrate whatever the equation phase generated here by a time period thus, and it absolutely comes here. Now once a day, whatever the value has come, the multiplication from here, we'll be making threshold 0, as simple as that. Threshold is 1. It compare the output of this with the threshold, compare the output of the threshold 0. If it is, this is greater than this, it assumes that yes, it is a 1. If it is less than this, and it assumes that whatever the deducted is information, this is exactly called estimate. This is exactly called coherent deduction. Please mind it, in the QPSK, how to define it in a 2 point. 1 point is 1. Each bit will be each signals. For each bit, there will be 2 bits. Even though, because the frequency of the QPSK takes an integer value, that is why we call as a die bits. How the QPSK is generated in generally, whatever the let us say symbol 10 you want to send it, so it will be have 10 for each bit will have 2 die bits, and each bit for 2 die bits for one symbol to be passing 1, and 2 die bits for a symbol to be passed, that is 0, 4 bits. In that exactly the signals will be converted into what? Odd and even, and odd and even will be multiplied, sum together will get back to similar. So similarly, QPSK transmitter is generated, as I mentioned, QPSK, this is as simple as that, but only thing is as simple as the BPSK, but here we are used the 2 lines. One is for, this is exactly called as in phase. Look back, this is called as in phase, and this is for quadrature path. Okay, please mind it here. In even in the, this is also, this is in phase quadrature. The 2 signals will be generated at the transmitter. That is in phase signal, and this is exactly what quadrature phase. Each wave by basis function will have a different phases. Okay, so similarly here at the receiver also in phase functions, and this is exactly what out phase functions. That is a quadrature phase. So similarly, we'll have next class we can going to complete what we call error of probability of QPSK, and then we can go for what we call it as MSK. Then we complete the BPSK by tomorrow classes. Okay. So if you have any kind of a doubt, please mention it, because I know this is all quite difficult as this, because only way we have to do it, I'm doing. If you have any problem, please report to me. Okay.